So the first thing we are going to go through is charge. Charge is the most basic idea in electricity. We use a Q to symbolize the charge, and the unit of charge is Coulomb, which is big C. 1 Coulomb of charge is really a big amount. We should remember this. The charge could be either positive or negative. So we could write it like Q1 equals 1 Coulomb and Q2 equals minus 2 Coulomb. The minus here means the negative, which is obvious. So what if we compare the amount of charge of Q1 and Q2? So will Q1 be bigger or Q2? The answer will be Q1 is smaller than Q2, although 1 is bigger than minus 2. When we compare the amount of charge, we only concerns the absolute value of these numbers. The positive and negative sign only serves to distinguish the kind of charge, not the quantity. We shouldn't be confused by the negative sign when comparing the amount of charge. So the next thing we are going to talk about is the addition of charge. Though the plus and minus sign means the kind of charge, we do need to consider the minus sign as negative when adding charge together. That's because the neutralize of charge. So for example, we have an object of 2 Coulomb and another with minus 2 Coulomb. And if we let them contact with each other, we will get a bigger object with 0 Coulomb charged. The plus and minus sign actually neutralize each other to form 0. So when calculating the addition of charge, we could use the most basic addition, like 2 plus minus 2 equals 0. And this could be applied to all. So for example, we have an object with 3 Coulomb charge and another with minus 5 Coulomb, and we combine them together, we will get a bigger object with minus 2 Coulomb. It's again 3 plus minus 5 equals minus 2. So let me now go through 2 examples about charge. The first one is an electron. An electron is negatively charged. The charge of an electron is minus 1.6 times 10 to the minus 19 Coulomb, which is really small. We also call this amount of charge as elementary charge because it is the smallest charge possible. We use a small e to symbolize the elementary charge, and is again equal to 1.6 times 10 to the minus 19 Coulomb. The second example will be the glass rod and silk. So if we rub the glass rod with silk, the glass rod will be positively charged and the silk will be negatively charged. The essence of this kind of phenomenon is the transfer of free electrons. So when we rub the glass rod with silk, the electrons will go from the glass rod to the silk. And as the glass rod loses something negatively charged, it becomes positively charged, and the silk becomes negatively charged. There is also a rule, the conservation of charge, behind this. We will first talk about the conservation of charge and then back to this example. So the conservation of charge means the net charge in a closed system will never change. The net charge here means the numerical sum of all charges. So for example, let's say we have a box and we have 3 objects in it, which have 1 Coulomb, 6 Coulomb, and minus 3 Coulomb charge. So the net charge could be calculated simply by adding 1, 6, and minus 3 together. We will get 4 Coulomb here. And this will not change no matter what kind of manipulation I did to those stuff inside the box. For example, if I combine the 1 Coulomb object and the 3 Coulomb object, we will get a minus 2 Coulomb object. Well, as we calculate the net charge, we will again got 4 Coulomb. It's just the commutative law of addition. So now let's go back to the rod and silk experiment. Because the number of electrons lost by the glass rod is equal to the number of electrons gained by the silk. Because electrons can disappear, the quantity of charge is the same between the rod and the silk. So the only difference will be the negative and positive sign of the charge. So it's like a x of a glass rod and minus x in silk. So when we calculate the charge, net charge before the rub and after the rub, we will all get 0, since the glass rod and silk are all neutral before. So this again testifies the conservation of charge to us. So the next thing we are going to talk about is Coulomb's law. This is a really important law, and it lays a fundament for those other ideas later. So the Coulomb's law is about the force between two charged objects. So we see the formula here. F is equal to K Q1 Q2 over R squared. The F, of course, is a force, and the K is a constant. It is equal to 9 times 10 to the 9 Newton meter squared over Coulomb squared. And Q1, Q2 means the charge of the two objects. And R here is the distance between two charged objects. And you see that I use the word between, the force between two objects. This word is kind of important because that kind of force is not exerted by one charged object to another, but between them. It's an interaction force according to Newton's third law. And about the R, the distance between two charged objects, there is something really important that you should notice. So let's say now we have two spheres, and I'm going to find the force, try to calculate the force between them. So what is the R here? What is the distance here? Will it be the distance between two surfaces or the distance between two centers? You might think about it for a while. And the answer here is the distance between two centers. You might not understand why, because, I mentioned it is a sphere, and those charges are distributed all around the sphere, so why not the distance between two surfaces? You might slowly understand this when you learn deeper. You don't need to worry about it, just remember it now. And here I provided a table and a graph that shows some numbers about the charge, the distance, and the force. This might give you a more realistic view on the Coulomb's law. There's something you might need to notice in this table. So since the K here is really big, it is 9 times 10 to the 9, as I mentioned in the last slide, and 1 Coulomb of charge really means a lot. And it is really hard to get 1 Coulomb of charge in real life. We can see the force here as like when the distance is 1 meter and Q1 equals Q2 equals 1 Coulomb. The force is really big. It is 9 times 10 to the 9 Newton. And you might try to calculate the gravitational force between two objects weighs like 1 kilogram or 1,000 kilograms in 1 meters, 100 meters, or 10,000 meters. You might see then that there is a huge difference between the gravitational interaction and the electrical interaction. The electric force is really much more stronger than the gravitational force. And on the right down corner, there is a graph of force against distance when Q1 equals Q2 equals 1 Coulomb. As you can see, the SR approaches 0, the force is approaching to infinite, and the force really died out quickly with the increase of distance because there is an R squared under K, Q1, and Q2. So the next thing we are going to talk about is the electric field. The idea of electric field is really important, and it's crucial to our understanding of other knowledge later. So we see electric field is a field that is produced by a charge. This seems a little bit redundant, but you might ask yourself, what is a field? This is not an easy question to answer. So we made an analogy of field to a function fx. The domain or input of this function is position, and the range and output is a number or a vector. So from this we should categorize it into two kinds of field, which is a scalar field and a vector field, which respectively output a number and a vector. So for electric field, it is a vector field. Its output not only have a magnitude, but also a direction. So now I will just give you all the equations, and I will explain it in the next slide. So as we see here, the magnitude of electric field is equal to K big Q over R squared. The big Q here means the charge that induced this electric field. And the R here is just the distance from the charge big Q. So as we mentioned in the last slide, we could think of a field as a function. So we write this in Fr equals KQ over R squared here. The R is what we call a position. So you might ask, why position is only a R? As we see that a point charge is a symmetry in every position, so it does not matter what position it takes. It is just the distance from it that makes sense. Then about the direction, if we have a positive charge, the direction of electric field was pointing out of the charge, and if we have a negative charge, it was pointing into the charge, no matter what distance it is from the charge. As we see in the graph below, the direction of the arrow means the direction of electric field, and the density of lines means roughly the magnitude of electric field. So in the picture on the right, we see a larger negative charge. It has much more these lines than two pictures on the left. There is another relationship here on the left down corner, F equals EQ. The F here means the force experienced by a charge, an object of charge Q, when it was put into an electric field of magnitude E. Let me say it again. If we put an object which has charge Q into an electric field of magnitude E, it will experience a force F, which is equal to EQ. So if we just plug in E equals K big Q over R squared, we'll get the Coulomb's law here, which is equal to K big Q small q over R squared. You might be a little confused when I change the Q1, Q2 to a big Q and a small q. I'm just want to stress that the big Q is a charge that induced the electric field that I'm talking about, and the small q here is the charge that I put into that electric field produced by big Q. It is not to say that the small q cannot produce a electric field, but it's just the perspective we are taking. We're just talking about the electric field produced by big Q now. Now on the next slide, I juxtapose these three equations together. And let me stress it again. The big Q is the charge that produces the electric field we are talking about, and the small q is the charge we put into the electric field induced by Q. So that's why F is equal to E small q, and E is, or the electric field is equal to K big Q over R squared. So why are we doing this kind of manipulations? Coulomb's law has already been very perfect, so why we will invent a electric field here? We're just separating the Coulomb's law. So what we are doing here is we just intentionally set one charge as the central one and perceive the force as the interaction between the field induced by the central charge and another charge. It's just about the perspective we take. So for electric interaction, we cannot just measure the influence of one charge solely. We always need to use another charge object to probe. The electric interaction is therefore always characterized by Coulomb's law, which consists of big Q, what we want to know, and small q, what we use to probe. Well, the introduction of electric field, except the influence of the probe charge by extracting only the terms that are about the charge we want, big Q, and the position from the Coulomb's law. So this idea allows us to study solely on the influence induced by one charge only. So that's why we invent the electric field